empirical engineering works. I don't know if you know what the word imperial engineering means, but what it does mean to us is we try something. If it doesn't work, just move on and get something that does. And you try enough times, you will come up with the correct solution. That was the whole science behind it. And the science comes with the patience and sticking with it. You just keep going. You don't give up. You're thinking outside the box every day. And it's very exciting to me to be able to say I've relived this as a result of this presentation. I've relived this for Sam, and I thank you very much, Sam, for inviting me to talk to you, because I like to talk about it because it's good stuff. Okay. Now, I've got a book here that's got a lot of pages in it. Cassandra's going to try and follow me with the book, because that's all I know is what I've got in the book. I wrote this as a result of my children telling me, Pete, put it down. I did about 10 years ago. It took me a couple of years to actually put it together, to find all the stuff and whatever. I've got original photographs. This book is in the Smithsonian Institute with some other things, and it's also in the Spafford Museum in Spafford, Oklahoma, the Aerospace Museum out there. So it's available to general public to see it. All right. So what I'm going to do with my objectives, we had from April to August of 1965 to complete this antenna system. Now, it came to us second-handed because the first company that bid on the contract got the contract, Delmo Victor. And Delmo Victor was totally unprepared to fulfill the obligation. So we got it as a secondary contract because our company, International Harvester, which I was part of, was able to, with the High Metals Technology Laboratory, which I worked in, we were able to satisfy the contract. And the major objectives we were given, if you can picture this now, 60 people in our particular group, 60 people sitting there, all waiting to find out what our director had done to us. Okay, and the scientists walked in and they talked to us for a while, did some mathematics on the board, did some crazy stuff. They turned around and said, 3 pounds. That's all you've got, 3 pounds or less to build this antenna system. Okay, we'll deal with that. 3 pounds or less. That's what it represents. Okay, less than that. The other requirement, 30 inches in diameter. And this is about the ruler we used too. I mean, it wasn't fancy if you started, guys. Okay, but that represents how big this thing actually is. Now there are 4 of them. Okay, so that's what makes it called high gain as far as the antenna is concerned. So the third one, and I want you to remember this word because I'm going to ask somebody out there to define it. The word indestructible. Because we were sitting there and we're all looking back and forth at each other. They said, the third thing came out, it has to be indestructible. What are we going to face? We don't know. What things do we have to be prepared for? We don't know. Go for it, guys. Our director got up in front of us and said, all right, you got all the information you need. Let's go build it. That was it. So I'm going to give you a little bit about what's going on. We had no internet. That was, who said that? So we had no Google. We had no AutoCAD. I don't know if you people know what AutoCAD is, but that's a computer-assisted drawing. We had none of that. So we had people who know how to draw. We had no lasers. We had no calculators. We had no CMMs. You know what that is probably. Intermittent wipers hadn't been invented for our cars yet. Okay. We had no cell phones and a lot of everyday things like duct tape, Ziploc bags, all these things were not invented yet. They were invented within the Apollo program. They were all quite secret. I mean, I had things I couldn't talk to about my wife and we were using them in the kitchen. You know, they weren't there yet. Okay. Things were being patented and whatever. But we had highly skilled machinists, not operators. Everybody was a machinist, and you people probably understand that. There's a difference between a machinist and an operator. Button pusher versus a guy who knew what's going on and made it, okay? And we had sheet metal mechanics. You know, those guys that could design pieces like that, and they'd all fit together and go around corners and up and down and everything else. They could do all that. Okay, and they had a complete shop to do all that handwork, but they had people that knew how to do it. All right. We had no slide rules, okay, and we had no drawings. Can you imagine that? We built this without a drawing. Just think about that. We communicated. We draw a sketch on the blackboard, piece of paper passed from department to department. That's how we communicated. Oh, we needed 30 inches. I know what that is. I got a ruler. You follow me? I got a scale. I know how to use the scale. Okay, I know how to use micrometers and things like that to measure things. All right, and the individuals that we had were common people that the janitors knew as much about what we were doing as the guys that were actually doing it. All right, because they had to clean the heads, and they knew what chemicals not to deal with, and they knew what was good and what was bad. How do you do this, and what is a clean room? They all knew this. There was no, no hesitation. They all knew how to do it. So all the way from the bottom, so-called, to the top, were all skilled workers at what we were doing, and excited workers. They enjoyed what they came in to do because they're doing things that were never done before. Think of that, never done before. And then we go from there. Okay, I'm going to go into give you a little bit of my background, okay, just because I want to let you know what I'm talking about. I started with, high school and stuff. I joined the Marine Corps, and I was on the aviation air wing. I was fixing planes. There's a picture up here on the front shows the kind of plane I was using. I was working on. It's the F-8U Crusader. It's the fastest, over 1,000-mile first aircraft fighter plane that was over 1,000 miles an hour with a single pilot. It was nothing but a fuel tank and an armament and a pilot. Okay, and we were trained to, in my particular case, I was a structural engineer, mechanic, whatever they call this. And I was in charge of airframes and various other components with just the aircraft had to fly. Not hydraulics, not tires, not radio or anything like that, but just the physical aircraft. If it got a bullet in it, I had to be able to know how to fix it. Something fell off of it, I had to know how to fix it. I was the first line of pilots that got torn up or had accidents in the field. We had to get them back to the carrier. So there was a base that they always had all the right people in that base, just an emergency landing field. They would fly into the emergency landing, hey, I got a problem with this. There was certain people there that could take care of everything. The principle to get them back to the carrier back home because they didn't want our planes going into the water. So that's where it was. So after serving 4 years in that, I went to the University of Vermont. Sort of unsettled there, was not going on. They came out and said, we're going to the moon. That changed my whole attitude. So I transferred to Vermont Technical College. I graduated with honors. My first job, my first real job, paying, I don't consider the military being a job, was working with this high metals technology laboratory, Division of Aerospace and International Harvester on the West Coast. That was my first job. It was crazy. Here I am, I'm 30 years old, but that's okay. And going into this program, totally unaware of what I was going to get into, but they said, hey, Pete, you've got your Marine Corps background. I was a qualified machinist at that point. So I was able to do certain things without being trained or taught anything like that. So they said, build us a model of what we're trying to produce here, and we'll send it to NASA and show it that this is our concept. That was my first job. And they handed me a sketch. Basically, it was 4 circles. Okay, 4 circles. Now, Cassandra, hoping we got all this other right, you can probably show those 4 circles on the screen up here.
We surely can.
We'll see if we're doing it right. You follow me, Assam? Okay. So
yeah, we can hear you loud and clear and see you, and now we're starting to see the
find it?
pictures. So thank you, Cassandra, as well.
Okay, is it coming up there, over there? No, you had it. You had it. No, go back one.
Thanks.
Back. There it is.
It just brought their own up.
Does that come up on the screen there?
They can see it. He's getting it.
Oh, they can't see it? Okay.
We're getting to it. Just keep talking. You're good.
Okay, all right. Well, this is the model that I produced to satisfy the contract arrangement that they had made, because it was a subcontract, because the first company couldn't make it. Okay. We, my directors said we can, because we knew what we're doing. We're not messing around. Now, that was the model that I made. Okay. And that's what it looked like. Okay, basically, without any modifications or changes. That's what was submitted to get the contract. All right. So again, my background, after exciting period of 5 years in San Diego, I returned back to Vermont and started a small business with one man, ended up with 25 employees manufacturing, producing stuff for the mail order catalog industry. And I have 2 patents to my credit. And then I sold that business in 1989 and retired at 50, which was kind of cool. All right. And I'm enjoying the fruits of my labors and did all those things that retired people do: sailing, classic cars, long distance hiking, traveling. I enjoyed, never looked back. I'm 83 years old now, living in Mount Airy, and I'm playing the 1-string washtub bass with local musicians, and I'm enjoying every minute of it. Okay, now we're going to get into the meat of what I actually was doing. Remember, this is not one person. This is a team of people. Okay, each particular thing had a team. We had a mission statement, first of all. You figure to find a mission statement yet? Okay, that should be your photograph here, whatever that is. Mission statement is that thing you've got up there. That's what it looks like. All right. Well, again, we're new at this, so give us a break. Okay. She's got it there. Okay. Okay, just keep talking. She says, shut up and talk. Okay, what we had to do with this, and this was told to us by the scientists and the people who were really up on the top end of the Apollo program. We have to do this. We have to communicate with Earth, Houston, space module, service module, and the moon. It's the first time we've ever had to communicate 3 ways. Never had been done before. Apollo 8, back and forth, back and forth, back and forth, no problem. All of a sudden you enter another illusion. What are we going to do here? Whoa, we got to do something. Can't just do what we've done in the past. We have to do something brand new. That brand new thing required what they call high gain. High gain meaning there are 4 disks now instead of 1. That means we're going to try and get all the information we can, pull it on one particular point with a parabolic shape, and then send that piece of data wherever it's going, either on the moon, back to the space capsule, or back to Houston. So that communication link was just incredibly important. Without that antenna, none of the information that they were gathering or communicating back and forth, how to get back or anything, would not have been done. So it was considered mission critical for this antenna. We had, now remember those 3 things: 30 inches, 3 pounds, indestructible. Keep that indestructible in your brain. Okay, that's cool. So that's what the mission statement was. It was, I'm not saying easy to accomplish, but it was something we knew we had to do it. Okay, and in order to do that, we formed teams. Our director said, all right, guys, we're going to put the right people together to do the right thing. And each little team will solve their particular problem and pass it on to the next team, and they're going to develop it a little bit more. The next team will add something to it, and we just keep going with those teams all the way going through. So we, first of all, and there's no particular order to these because they're all very important, all equally important. Nobody did one job that was not important. The material selection. What kind of material can this be made out of? It can't be made out of wood, burn up, probably float in space. We don't know what would happen if it was made out of wood. So it had to be some sort of a metal. Couldn't be heavy because it wouldn't conform to the weight restrictions. Had to be strong to be indestructible. So all these things came into play. So the top metallurgists in the company, okay, they put together the type of material that it was supposed to be. They found, they did their research, they did their experimentation, they did all the things, and it turned out to be a Rene 41 material, which nobody had heard of. It was manufactured in one company in the United States. But that was the material that was selected that would satisfy all the requirements that they could imagine. Okay? Now, once they determined that, they passed it on, that information, Rene 41. They found out they could get it as a supply material. They found various things and all that type of thing. And then after that, we went for various other things that the team had to solve. Once we knew the material it was, we had to know if we could braze it together. We had to know how we would fasten it together. We knew different things. It had to be lightweight, so it couldn't be. The material we ended up using was 1,500 thick. That's half the size of a human hair, which is cool. I mean, if you had instruments that you could make to measure that, okay, but you're getting pretty close to the end of it at 1,500. And it had to be strong. It had to be, well, it was lightweight, but it had all the material characteristics that were necessary to solve the possibility of indestructible. So just imagine all of that. Now, how do you take 1,500 material and put it together and make anything with it? Now the different teams started coming into it. Each team had a specific goal to say, how can we tool this up to make it fit? How can we tool it up to make it work, to be able to assemble it? They made tooling that would accomplish the total mission of 33 units. So the tooling would stand up to 33 units. And there was over 200 linear feet of this material that had to be made, but I'll get into that a little bit more. The configuration of the material had to be strong, obviously, to fulfill some of the other requirements. It had to be very strong. So it had to have a configuration which would allow it to be strong, which is some form of structure, all right? And the way it was put together, so that all those things went together to figure out exactly how that went, okay? The assembly method, how do you assemble this stuff? I mean, it's kind of dramatic. That's where I started to come in, okay? Once we knew what the material was and the various other things, we then went from that particular configuration, developing the tooling and the various things that were necessary, that we would be given, myself and Dick Messer would be given this material, and we would literally assemble this particular unit. Now, in order to get there, we had to have a little bit more information. So we started working on what we called a eutectic alloy, which was my part of the program. And that was developing an alloy that would braze Rene 41 to itself, okay, and be contiguous with a solid environment. In other words, it would braze it well, it would do a good job, and it was lightweight, and it would all work together. Developing that took me about 6 months to do with that, to kind the right alloy that would melt one time at one temperature. The next time, it would not melt at the same temperature. It would melt at a lower temperature. So variously, the eutectic alloy would be able to satisfy 3 braze cycles without destroying the first 2. You understand what that says? You put something together with butter, and the next time you bring it up to butter temperature, it all falls apart. So all your pieces are on the ground. So the second time it had to go, and those 2 braze joints had to stay good while you braze the third one. Okay, so that was a very critical part of the whole thing. And that was my involvement, the total brazing and assembly of this particular unit, after all the other things. Machining was done by the machine shop under our supervision. That was all different things that we had to do, and I can explain that more thoroughly. Testing lab, after we were done, we all wanted to, we passed all the tests, okay, that we could do after we had completed this unit. We all wanted to take and play it like a Frisbee, but they wouldn't let us because there was only one. There was only one that we proved right. And they wouldn't let us throw it off and play like a Frisbee, okay? So after all these things that were done, there were almost 300 or 200 linear feet of core required to do this. 64 braze joints per foot, okay? Calculated roughly to 12,800 brazed joints per antenna, 30-inch. Okay? 40,000 resistance wells, including the spider and the ring. which you saw the spider was that thing that went out from the center, and the ring was the outside diameter. Okay, 40,000 resistance wells. Okay, it created its own problems. You know, right here sometimes. Okay, so the development of the alloy was, I told you about it, it was a tedious process. Anytime you guys get a question you want to do, save it a little bit, remember what it is, and we'll get to them at the sort of at the end, okay? All right, in order to braze this together, we had to use techniques that were not really chosen before. This is very delicate material. We had to have a carbon mold made up by the machine shop. That was the only time they had a dimension in drawing, because it was a parabolic shape that they needed to conform to. And once that shape was figured out to be the correct shape for the antenna, they made the configuration out of carbon, solid carbon, a male and a female mold. You'll see the picture of them. We made or put together the male mold, okay, was the part which we laid the core up onto that mold. That would give us the shape. Then we did the little weld joints to make all that stay together. And we used it also in the brazing cycle to bring this whole unit up to temperature slowly. You know about heat treating, some of you, and bring that whole thing up to temperature slowly so that we could put a little vacuum on it and suck it down into its position and all that stuff, and hopefully not crush the material. That's a whole different process. That was a team before us determined the crush cycles and the various other things that were going through it. So all this information started to come together now. All right. So we were able to put that brazing situation together, and that was preparing it for a vertical turret lathe. I'm not sure if you know what that vertical turret lathe is, but it's a lathe which, instead of laying down flat, which you probably understand, a lathe laying down flat on the table and your chuck is going around this way. A vertical turret lathe is the table is going around this way, and all the tool is coming down from the top. Okay, so you'll see, okay, I'm going a little backwards here, but this is how on the next page on here, this is item number 7 or number 8, which we're looking at. This is how the core was laid up on the mold. Okay, we don't have that picture, but if you take the one that you saw with the female mold, we're looking now at the picture of the female mold. That's when the machining is actually taking place. The vertical turret lathe, you can see the big heavy carbon block there, and that revolving EDM head was where we cut it with no burr with the electromagnet or electro machining. EDM they call it, electrical discharge machining. And that never touched the actual work, but it cut it without a burr. They use lasers now. They don't have lasers then. Lasers weren't around yet. They were still thinking about those in some laboratory. So we used EDM, which was new at the time. So the core was laid up, when it came down in its shape, you're laying around a circle with a single strip of material, okay? And putting this core in between it. It's wrapping around. So you're going to get a little bit lower each time you go around. And it's all going to stand up like this, where you've got this overhanging the next one. You follow what I'm saying? So it's overhanging it. That's not acceptable. It had to be machined in order to bring that all down to the same plane, inside and outside. We had a dimension for that. The machinist had the profile to do that. So they were able to accomplish that. But in the actual machining process, which is the thing that we have on the screen there now. No, we're out of sync already. Okay, this right here. Pardon us. We're learning. There it is. There it is. Okay, that's the machine doing the work. It's filled with beeswax to help it be stable. It was heated up, beeswax poured into the cores. Then the head never touched the metal itself inside that machining process. It was like an arc welder. You know what that is, how it sort of disintegrates the material. It's a little bit different, but the same principle. So it never touches, but the electro process disintegrates the metal so that it's just gone, turns into, dust. But it never touched this. It would leave no burr, which is the most important part. The curve of the antenna was thicker at the top and went down narrower. That gave us ability to take weight away from it. The engineers came up and said, from the structural standpoint, we can go with this dimension in the bottom, this dimension on the top. Somehow you match them up with the same dimension going for a parabolic shape. Understand what I'm saying? You sort of follow it? Sort of? Okay, so it's thinner. It's thinner at the bottom, like at the top. The top, in other words, it comes down and gets thinner. So it doesn't need to be as strong out here as it does in here, because it's, whatever. But again, this was part of the structure. Now, once the thing got machined, it was basic after it was brazed. I mean, the brazing process, I'm getting all out of sync with probably Cassandra, but we're all right. We just showed all the pictures at the end, whatever, it doesn't matter. But the process to get it to this particular point after the brazing, we had to bring this up to a little over 1,000 degrees. Everything got red hot. Okay, you know what red hot metal looks like. It's just kind of flat, it's just kind of like spaghetti. It just doesn't really want to do anything. It was welded, but before we actually put the thing in and braze it, it was like this because it wasn't solid. We had to make this unit come out as one piece of material. However, it was fabricated by all these pieces. That was the objective, to put it into that shape. That's part of the indestructible part of it. So it was one piece of material after it was brazed together. You couldn't do anything with it. I mean, it was one piece of material. Okay. And once we got to that, then we had to go and put all the other superfluous things that went with it. So some of these pictures that we've got here, okay, showing it being put into what we call the muffle box, which was a stainless steel envelope that this whole thing fit into. We fed argon into that while it was in the furnace to keep a clean atmosphere. We had a vacuum on there so that when we got it up to temperature, we pulled the vacuum on it and sucked that top part of the muffle right down to form to the finished machine process. Okay, we were wondering if that wouldn't distort the whole message. We didn't know what would happen. Okay, it never been done before. See, all these things never been done before, but we practiced on little pieces, a lot of practice. Okay, we did lots of little things to make it so we felt comfortable it wouldn't crush. With a 1,500 thick down to less than 1/4 of an inch on the outside, pulling a certain amount of negative pressure on it at red hot temperatures, what's going to happen to this thing? Is it just going to all suck down and go away, or are we going to come out with a good part? We didn't know that until like 72 hours after, because it took that long to cool down because of the heavy carbon block. So we're just sitting there like this, waiting for something to happen. Finally opened the box, to our not amazement, because we were confident. We wouldn't have gotten that far if we weren't confident. Everything worked perfect. We had a good part. Hooray, the whole department, hooray, we did it. We made the first part, okay? Now, there's a lot of questions in between. You got any offhand? You got any questions offhand before I ask you my question?
How did you know, was there any way to test the indestructibility?
Well, I'm going to get to that.
Repeat the question when they ask it.
Yeah, what's that?
So you had to repeat the question because they.
Oh, okay. The question was, when did we determine things that were indestructible? How did we determine that? I'm going to save that answer for a little bit later because I have some definitive answer for that. All right. But that's a very good question, because that was the question I was going to ask. The question I was going to ask you people, how do you define the word indestructible? How do you define it? Good answer. Do we agree? Good answer. Can't not be destroyed. Okay, that's a good answer. Thank you. All right. There's things, like I said, when we tested this, I don't know if you know what a vibratory table is. It's a piece of granite. You probably know about granite. And it's put on a machine with a cam on it. And you turn on the machine and you make it go boom, boom, boom. And it just goes back and forth. Well, you put it at certain frequencies and all of a sudden you've got this harmonics that are going on and it goes in crazy. And you can literally disintegrate certain pieces if you put them under the certain things. And the company International Harvester was using it to do testing on gas turbine engines when they were getting into building those types of things, and balance and all these other things. So we put it through those tests. We put it through all sorts of heat tests. We put it through all sorts of other tests that we could imagine. Like I say, in the lab, once we got through with this whole mess, we wanted to throw it out in the yard like a Frisbee, see what it would do. And they said, no, you can't do that because we only got one. We got to have it. Okay, we need it for the rest of the process. Okay, but we wanted to go out because we all knew it would happen. We wanted to throw it against the wall, like a Frisbee, and see what would happen to this thing, because we made it to be indestructible. That was our objective, but we couldn't define what it really meant. Okay, and so we had been successful in all these things that we got involved in. Everything was really cool. And now we had this testing machine and we vibrated it to death. I mean, just vibrated it to death, but nothing happened. And the only way we'd keep instrumentation on it to decide whether we were really vibrating it enough or not, okay, was something that was developed by Eastman Kodak up in Rochester, New York. It's called super glue. They called it Eastman 910 glue, which was very classified secret stuff. Okay, we call it super glue now, but that was the only material they could find, or we could find, that would stay onto that antenna under those vibratory conditions that wouldn't fall off. They sent us our laboratory, they sent it to us by the gallon. They said, play with it, see what it'll do. Don't touch it. If you put it on somebody's chair, they're going to stay there. You follow me? And you all know about that now. They glue things together in surgeries and all this other stuff with super glue. But we were told very specifically, it does get to be dangerous if you don't play right. We used to glue people to the floor. They'd walk, we'd go from office to office. We'd put a little strip of super glue on the floor. They'd walk out there and stop. It just stopped right in the middle, like, whoa, what happened? We, briefcases to the floor, newspapers closed, all that kind of stuff. Think of 30-year-olds. That was pretty much our average age, 30-year-olds, given a toy that nobody knew what would do. And they were all kind of engineering guys. And we all had a good time. We had lunch times and all that stuff. And we went a little bit bizarre with it. Let's face it. And it was fun. I can't remember all the things, but glue the skin on a peach. Can't get the skin off. What the hell's the matter with a peach? Bananas. You can't open a banana. What's the matter with a banana? It works on everything. See? So those are the things that we had to play with. Now, you saw the 3 pounds. There's the 3 pounds. Okay, typical cabbage weighs 3 pounds. Okay, and the 30 inches, that's how big it was. Okay, so we got a picture here of a nice, beautiful little 1965-year-old chick hanging onto this antenna, showing how lightweight it is and how big it is. And she's got, there she is, see? Just to show how that we had accomplished those things. We still have not accomplished the indestructibility portion, have we? We haven't decided that yet. Okay, well, I'm gonna sort of give it away at this particular point. I want to say that a guy named Jerry Woodfill was on the telemetry television screen on Apollo 13. Okay, when they had the explosion. He was the only one in the world that saw this firsthand. He's watching it. He heard, Houston, we got a problem. At the same time, he watched 13 square feet of material go right into the antenna. His report after that said, we know it was about 30 inches in diameter. We know it weighed about 3 pounds. And I believe, by my engineering background, it is indestructible. Now, he never heard the words that we got in the laboratory to say it was indestructible. But he used the same word that we got, which was, to me, after 50 some odd years, that was the solution to the problem, which was so incredible to me. And this happened because of a friend of mine walked up by my house in my area and said, hey, Pete, how you doing? We talked about the antenna business because he was interested. And he came up with this article of this Jerry Woodfill that had written like 4 or 5 years ago. Okay. It was my first understanding. I tried to get a hold of Jerry Woodfill down at NASA, and he passed away this last January, and I wasn't able to get in touch with him. I sent letters, all sorts of stuff. He was probably in some sort of a home or whatever, but I don't know. But he said it was indestructible, and I got it in writing, which is cool. I mean, you probably might not understand how in-depth that goes, but I worked for a nice period of time in my life on this and never knowing if it was indestructible or not. We never knew, but it did satisfy all Apollo missions. They all got burnt up, but there's one left, and that's in Stafford, Oklahoma, at the Aerospace Museum. It's out there. I was sent photographs by the director of the museum out there and asked if those photographs were the actual production model. And I verified the fact that it was through those photographs showing details of the braze joints, details of a lot of stuff. Okay. Now, so that was, you might say, the conclusion of that whole thing for me. I put it to bed now as far as it's conformed to all the things that were asked of us as a laboratory item. Okay. And there's one left, and that's in Oklahoma. Someday maybe I'll go out there, but I don't know. They've asked if I would go out and give a little talk about it when they're, in front of the antenna itself. I don't know if I'll, do it or not, whatever. But the excitement that was developed around this particular successful thing, okay, it was very good. It was one of 13 issues. It was number 8 of the 13 issues. The Apollo 13 mission would have failed catastrophically had that not been a part of the overall success rates. There were, but it was number 8 of 13, which is pretty high up the line. Okay, as being the most important thing out there. I'm sure one was they ran out of oxygen. I don't know what the others are, but I have the article, but I've never bothered to really read them. But being one of the top 10, I think is kind of cool. And I was very instrumental in the final stages of that whole thing. I worked with all the different teams. I had an explosion ingot developing the alloy, almost lost my vision. I'm a member of the Wise Owl Club, which is Prevention of Blindness organization. I've got pictures in my book here. And then I'll throw this out. I know Sam isn't here with his crew, but I'm sure that you might have seen those pictures in your notebook or whatever they have. It was all very real. It was very real. And our realization to the whole program, I don't know if anybody else is alive that has worked on that particular antenna program. Okay. I don't know if anybody of my people that I work with are alive. I'm 83, so they got to be, I was 25, 30, right in that age when I was there. So you had to have been born. My kids are older than a lot of you probably. It's whatever. So I really want to get some questions. You give me something good to work on, because I can talk all day on this. And if you're interested in getting specific with it, I've got some little toys up here. This is something you can't even see it probably. It's 1,500 thick material put together as one unit. But don't try it the other way. It's indestructible. You have to smash this whole thing to death and you won't get it apart. Because I've done it. That's just a little piece they let me have. Here's another piece showing some of the structure after it had been tested to try and crush it. I mean, it takes tremendous pressure to crush this corrugated material of that thin a material. You could not bend it. You throw it on the floor, it would not bend. You couldn't take it like this and do anything. And it's this big around. You took a single sheet of material, you can go like that and you can make it go. Right? Not that. Okay, because each joint, now in order for us to identify each other's work, myself and Dick Messer put this whole thing together. We were selected to put it together as a team because we were compatible, number one, with each other's working habits. His skill levels were different than mine, but complemented his, and the same way go back and forth. So the two of us worked together like a well-oiled team. He was about 8 years older than I was. And we trusted one another's work. We trusted each other completely. Every joint had to be at least checked 3 times visually by one of us. Okay, so that we knew that his work was good. He knew that my work was good. And we used Q-tips with different colors on them to identify where we were in this pattern of corrugation. I'd put my little red one, he'd put his green one, okay? Then we put a yellow one, says we got to check this one. And all these little things that we worked out together. The most difficult part of the actual assembly of the raw materials, meaning the core and the strip, okay, was to get the strip straight so that when around like this, it didn't go up, it didn't go down, because you couldn't bend it either way. You can bend it the easy way, but you could not bend it the hard way, which is against itself. You couldn't. So it had to be 90 degrees vertical on the mold, okay? And if it wasn't 90 degrees vertical and it went like that, it would go and it would go like this and get worse and worse and worse as you got out. And you got 200 linear feet of this. That was the most difficult part of the actual assembly, to get that fixtured right so that it would not climb. We're talking within half thousandths. Okay. And measuring tools with vernier calipers. Okay. No digitals. Okay. Micrometers, just the way you'd see a micrometer on the shelf somewhere. Okay. Vernier protractors. Who's ever heard of a vernier protractor nowadays? I mean, it's all just lines. Same way with the slide rule. You line the lines up and they're good. If you don't line them up right, you are not going to get the right answer. It just won't work. It has to be perfect. So you use your magnifying glasses and you do all the stuff. The old machinists here, they know what I'm talking about. It's kind of neat. But those are the tools. And if you're interested in coming up and seeing some of that stuff, I have a couple of the pictures here. I'd love you to pick this up and see how long that is and touch these things if you're here and you know, when Sam is gone and everything else. So Sam, I hope I have answered the questions that you would like to have me answer.
Yeah, I think you're doing a fantastic job. We have one question
the whole
on
thing. You would
online
probably
that
know more about the Apollo program than I ever will, but
I don't
we
know
made
about
it
that,
work.
but definitely excited to
Okay?
hear. I guess we had one
proved it
question
in
from
several different ways. We got all the guys back. Okay, we had trouble before the Apollo program. Okay, one tragic incident where we lost a spaceship, whatever. But on our mission, the Apollo, those antennas were on every Apollo mission from Apollo 8 up, which is, I don't know, 12, 15 of them, whatever. And they never failed. Communications were always perfect. There was a lot of problems with after the program. They actually lost the videotapes of things that came back over it. The reason why people were skeptical as to whether the Apollo mission was even real. They didn't believe it was, you know, it actually happened. There are people that still don't believe it. And the reason the antenna and the television situation, okay, we had differences in technology from United States television system. I'm not familiar with it. To the material that was coming back from space was far better than what you saw on television, because it was third generation, because they couldn't make it go to our television, so they had to take a picture of what came back from space, and that made it fuzzy. Then everybody, you didn't even go. Okay. Lots of arguments. I don't want to get into that kind of stuff. You guys at NASA know it. I hope that what I'm saying here is inspiring you guys to think of the unknown and all the stuff that just is insanely exciting, going to work every day and not knowing what you're really going to come up against. Because the experiment you did yesterday, sometimes it worked, sometimes it didn't. Then you get all mad and you say, oh, we'll try another way and do it. So using the empirical knowledge and the way and communicating, if you can communicate, develop a good line of communication with all the people that are working on whatever you're working on and stay with it, because the human knowledge is going to be the solution, not so much the computers. The human knowledge is going to go between the lines, out of the box, wherever you're going to go. And if you hear somebody that's talking about it and you know something they don't know, get in the conversation and tell them what you know, because it's going to help somebody somewhere along the line in what they're doing. And that's the exciting part of this whole NASA stuff. I mean, I'm 50 years out of it. Okay, but you're doing things now that are incredible. And you've only started. Now I have, knowledge of people that are working on some of the stuff now that have just gotten contracts. And they're kind of excited about it, but they're terrified because they don't know what they're going to do. You know what I mean? They haven't gotten there yet. They haven't solved that first problem yet. And they're waiting to figure out what that problem is going to be, but it'll come. And how am I doing with time? Am I all right?
You got a couple minutes left. I'd like to move to some questions. If you don't
Sure,
mind.
go ahead. Go question, please.
I have a question actually.
Real quick.
How much super glue actually made it into being used on the Apollo missions? Or did y'all just
The Apollo mission, I can't tell you, but what we used
Was the green?
is probably 3 or 4 drops. I mean, we had to glue something like this to something like that, okay, on the edges, onto that, okay? How much does it take? Doesn't take it all over. It's like the brazing alloy. Each one of these cells had to take an eyedropper with a calculated amount of alloy and a calculated amount of what we call binder to make the alloy stick to whatever you got here. Each one of those cells had to be touched with that amount to make it stick with the right amount. If you put too much, it would weigh too much. If you didn't put enough, it wouldn't stick. If you didn't get the right temperature, it wouldn't stick. All these things, if it didn't work, and here you are, 1,000 degrees, 1,500 degrees sometimes, all right, red hot material, inside of a box you can't see, trying to pull a vacuum on it, okay, so it won't crush it, and having enough alloy in there, and hope you put enough binder in the other parts that we're touching, it wouldn't stick to that part. You follow what I'm getting at? Just a horrendous number of little things, little details that had to be accomplished.
We have another question actually.
Yeah, go ahead.
So do all or only 2 of the 4 dishes have a little slice taken out of them?
Oh,
or
yeah. Yes, those
Are they
those
connected?
slices were, I'm going to call them aftermarket thoughts. And what we had to do was cut a corner of them off so that they would all fit within the desired framework, because they couldn't all come in touch. You had to pull them in a little bit, but the focal points, all they had to do is change those and they would all come to the same place. We had to make a saw cut and cut part of that antenna off. How's that? No burr. Cannot have a burr because that radio stuff will come in there and bounce all over the place. You wouldn't have a good signal. So it had to be cut off with no burr. I worked for several months to get what they call an EDM saw made. Never been done before, but I made one. If you get that picture up, you'll see the science that goes behind making something in a real research lab as opposed to these things you see on television. You see the floor, see the paper on there. I made that machine so that I could cut this material with no burr, because they had to cut that corner off. All right, now the next picture, if you can get it. Yeah, see that little white line between the two diameter reels? No? where I'm looking. See where I'm looking. There's a white line going between the two lower dishes. Can you not see that? Put your finger on it. Put your finger on it. Just put your finger on the white line between my eyes. Right there. See it? See the line there?
Yeah.
That's where it's cutting. I had a wheel on the bottom of the tank. I pulled it like this. Now, large diameter gave me ability to say there's 2 thousandths between those two lines. I could move 2 thousandths at a time by doing this. Raising the part onto the line that was going across was made out of Hastelloy X, all right, which would not deteriorate too much because each time it passed through the work, it deteriorated just a little bit. You'd lose 1 thousandths maybe of diameter. Okay. Now, the reason for that top part, the hardest part of that whole thing was to get that line, that piece of stainless wire, okay, long enough so that it would go through the entire length of what you were trying to cut without deteriorating too much.
And we have a follow-up
Yep.
to that as well. Are the dishes connected in parallel to one transmitter or each to a separate transmitter?
The dishes go into a solid core, it was a center focal point, which is the parabolic concept. Each dish focuses the material onto one point, which would reflect it into whatever they had. The electrical part of this I know nothing about, but it was all focal points, which are mathematically determined. The parabolic end shape is determined by form, and you just do that. They will know exactly what angle to put them, or if they get something coming this way, which radio beams is straight, I understand. Straight, this way, coming to one point, gain, now input it into the end result, which transmitted whatever they did. So that's, go ahead. What do you got?
I think that is the end of the questions we have on this side. But we have about 2 more minutes. So if you
2
have
more
any
minutes of
if you have any
questions?
if you have any final remarks you'd like to make,
What?
if you have any final remarks or anything you'd like to make,
Yeah,
that might be the
it was a
time.
real fun ride, guys. It was a real fun ride, okay? And 50 years later, it's still a fun ride, okay? Having to present this to Salman and his group, it was a very exciting experience because it got me to actually review the material again and just kind of live it all over again. And it's been kind of fun. So,
Yeah.
and I thank them profusely.
Yeah,
Well, thank you. If you
everyone
can
did for this
hear.
presentation with us here today. I know it was a little bit of a rocky start in the beginning, but thanks for hanging in there with us.
This is the very first one too, so there's gonna be some issues you have to figure out.
Yeah, there's going to be a couple issues, but hopefully we'll work them out. We had a hard time getting started today. But if we don't have any other questions, I think I'll conclude our presentation for today.
Okay.
And if
Thank you.
Sam, maybe you have anything else you need to jump in or say, I can let you do that. Other than that,
No,
you good?
yeah, we're good.
Did I
Thank
do
you very
all right,
much.
Sam?
Thanks, Cassandra, for everything was
Did I
great.
get
Mr.
it
Taggett,
done for you?
I'll talk to you. Yeah, I'll talk to you on the phone at some point to catch up. But thank you very much for giving us the talk, and Cassandra for making it all happen. And I'm going to stop recording the meeting too.
Alrighty.